combining equilibrium constants by adding equations. After you've completed this video, you will have learned how to add equations together. You'll see how you can find the equilibrium constants of one equation using those of those that add to it, and you'll learn how to manipulate equations, including their Kc constants, by either reversing the equation or multiplying through by a coefficient. What if we want to know the equilibrium constant of a system where we can't measure all of the concentrations? Well, remember back in the thermodynamics section when we were measuring enthalpy and we ran into the same problem? How did we solve it there? Well, we used Tesla's law in order to add the equations together to get a new equation. We're going to do a very similar thing here. Let's say we're trying to solve for this equation's Kc, but we can't measure all the things that we need to find it. Well, if we have these two reactions, and we know their Kc's, we can see that C and D will cancel out, adding to the final reaction. So if we know the Kc prime and the Kc double prime here, we can find the Kc of the reaction that it adds to simply by multiplying them together. Now let's look at what happens if you have two equations that could add to the desired equation, but only if you first reverse one of the equations. Now you can see here that if we reverse the second equation, we could cross off C and D to get to the desired reaction. If we do this, the rule for what happens to Kc is to invert it, or put 1 over top of the Kc. We'll look at why this is in a moment. Once you do this, you can multiply the two Kc's together in order to get the desired one. So doing this leaves you with Kc prime times 1 over Kc double prime. Now let's look at an example where we need to multiply an equation by 2. For this example, we'll use a real chemical equation instead of our generic ones. If we're looking for this equation's Kc, and we know the Kc of these two reactions, but now you can see in order to get the phosphorus trichloride to cancel, we're going to need to multiply the second equation by 2. If we're going to do this, it will definitely change the Kc. Whatever number we multiply the equation by will become the exponent on the Kc. So let's multiply the equation by 2, thereby squaring the Kc. Now we can cancel out the phosphorus trichlorides and multiply the resulting Kc's together. Let's examine both of these rules a bit deeper so that you can understand where they come from, which will help you remember them. First, why do we invert Kc when we reverse the reaction? Let's write a reaction in both directions. Now let's write out the Kc for both of these reactions. Notice how these two are related. Because the rule of products over reactants is how we write Kp or Kc, we can see that if we reverse the reaction, this ends up being the inverse of each other. So Kc prime would equal 1 over Kc, or Kp. Before we talked about multiplying the equation by 2 meant that we had to square the Kc. Let's think about this in a slightly different way. Mathematically, there's certainly another way to do this. Instead of multiplying one equation by 2, we could also just add another one of the equation that we need. In this case, the second one. Now, if we were to add all three of these equations together, we would have to multiply all the Kc's together, leaving us with Kc is equal to K prime times K double prime times K double prime. Of course, we know if we have K double prime times K double prime, or really anything times itself, that's the same thing as saying that it is squared, which would leave us with K prime times K double prime squared. And of course, if we had to multiply through by 3, it would be the same thing as adding in the third of the reaction, which would cube it. Now let's do a quick example. We'll try to find the Kp for the following experiment. If we know that the Kp for these two experiments are as follows, then we can take the second equation, multiply the whole equation by 2, which thereby squares the K, We can now cross off terms to be sure that we have the correct final reaction. And we can find the final K by multiplying the two terms together, leaving us with 1.89. So now we have seen how we can add equations together, manipulate these equations, and use them to find the Kp or Kc of a reaction that we may not otherwise be able to find.